All right, so what we're really after is B, right? The strain displacement matrix. It's the thing that takes displacement and turns them into strains. But of course we have this, Jacobian mapping in between because we're going to do the integration on the parent element and in terms of C and eta. So anyway, ultimately to update our stress, we have a vector and a matrix of material constants times the strain vector and the strain vector is XX, YY, to XY. And in terms of the displacements, then that you could write as, I'm going to write U sub X, so the X component of the displacement, the displacement vector is, the displacement U is a vector, it has X and Y components in 2D, right? So the X component of the displacement, partial X, is epsilon XX, right? The Y component of the displacement, partial Y, is epsilon YY. And then here we have the X component, partial Y, plus the Y component, partial X. Right? And so we could write that in a more matrix notation as something times partial U X, partial X, partial U X, partial Y, partial U Y, partial X, partial U Y, partial Y. Right. And so then that something, right? What I'm trying to, if I multiply that vector times something, I want that. Right? So the something is 1, 0, 0, 0, 0, 0, 0, 1, 0, 1, 1, 0. Everybody see that? If I multiply that vector times that matrix, so that those zeros and ones just allow me to pluck off the right entry such that I get the strain terms over here. Okay? So just in reference for later, we'll call this D matrix, D mat. That's what I called it in my code. So remember, that a component U of X that we're going to solve for, or the field U of X is equal to the summation of I shape functions over I unknowns, right? UX unknowns. So the UXI are the things we're going to solve for later. And then we have these shape functions. So because these are constants, this has a spatial dependence, but this is a constant. So if I take the derivative of both sides with respect to x, then that's just equal to the derivative of the shape function with respect to x. Right. Now, the way we write our shape functions are on a parent element. So the shape functions are written in terms of C and eta, right? But there's some mapping between, there's some mapping that's we're going to assume to be invertible, that, xc is some function of x and y, just like x is some function of xc and eta is some function of x and y, just like y is some function of xc and eta. There's some mapping between the physical coordinates and the coordinates in the parametric space. So just to sort of investigate, and I think we did this for the scalar field case. It's the same, but if we had that, if we wrote that, the shape function was some function of like because there's this relationship. If it's a function of xc, then I could just also say, I don't know exactly what it is, but it's some function. There's some function of xc of x and y that would give me x, right? So I could likewise write it like this. Right? So then if I take the derivative of this guy with respect to xc, so I'm going to drop all the functional dependence, but if I take the derivative of the shape function with respect to xc, then I have, via the chain rule, and likewise for eta, if I take the derivative with respect to eta, because these are things we can readily evaluate, right? We have a shape function in terms of xc and eta. We can readily compute this. It's these things we're seeking a solution for, but we don't readily have them available. Right, and so I can write that in matrix notation, or as a system of equations. And we'll call this J, right, the Jacobian determinant. And so this is actually what I want, so I can solve this system of equations, right? So these we can readily compute. These we can compute because, remember, x is in x, well, in I x I, right? So this is the field variable x is a function of the x positions at the nodes times the shape function. And the shape function is a function of xc and eta. So if I want to compute these derivatives, I can just compute them because they're just function. This is not a function of xc and eta. It's a constant. So we just take the derivatives of the shape functions, multiply it by the positions of the nodes, and I get the field variable x. And I can fill in, same goes for y, and I can fill in this J matrix. And then, of course, the solution to that I'm just going to write J inverse. Okay, so now I have what I need in terms of things I have readily available. So I'm going to go to the next page, but we're going to use this to substitute in to this vector, right? Because the field variable u of x is just the derivative, well, that gradient there, the gradient of u of x with respect to x is the gradient of the shape function of x times the unknown displacement. Right. So So that's nothing more than I had on the previous page, okay? I just rewrote the same equation. But that's just for my u of x. I also have uy's, right? But if we were to go through all the derivations, the same transformations would hold, okay? So I could also write here, just below it, my y component with respect to x, my y component with respect to y is equal to J inverse. Okay? And so, what? Oh, yeah, sorry. This should be eta c eta. Okay? Now, if you look, I'm going to go back. Look at this guy. You know, just remember it because we got to go to the next page. But you know, partial u of x with respect to x, partial u of x with respect to y, partial u of y with respect to x, partial u of y with respect to y. It's one vector. That's what we need. We need something to put there, right? Well, if I just stack those two on top of one another, that's what I have, right? Okay. Problem is, well, it's not a problem. It's just they just have to be consistent when we stack vectors and matrices, right? Such that we get partial u of x with respect to x. Everybody see that that's equivalent to the combination of those two things? So for future reference, and because this is what I called it in my code, I'm going to call that JMAT. Just understand JMAT actually includes entries that are the inverse of the original J. Right. So then I just need something here to replace this vector with that takes me from the unknown displacements into the field variables, in the field gradients. Right? And that's easy. Right? That's just partial N1, partial XC, 0, partial N2, partial XC, 0, partial N2, N3, partial XC, 0, meaning meaning it depends on your element, right? How many unknown nodes you have in your element are going to determine how big this matrix is. So it's just 1, 2, 3, up to n, where n are your number of nodes. Right? So then.
This way, it's like you're storing U-shaped functions for every other type of nodes. It doesn't matter because n1 and
Yeah.
it doesn't change. Okay.
And that multiplies our vector of unknown nodal displacements, right? And so I have ux1, uy1, ux2, uy2, ux3, uy3, to u n x u y n. Right? Okay.
The order of the second and the third change and the left on the left-hand side. So you said the ux, the a node, but then what it does is like it calculates the u, y, the eta. So the first row calculates the d, ux, the eta, PKC, right? But the second row calculates the d, u, y, the eta.
Oh yeah. Okay, yeah. So you're right. So I should change these, and I'm going to change these because I don't want to I'm going to change these because I don't want to rewrite the whole thing.
Yeah.
But it doesn't matter as long as you're consistent. What I should have done in that case was then put this row, swap those two rows, right, in the matrix. I don't want to rewrite the whole matrix, so I'm going to fix it here. But it doesn't matter as long as you're consistent, right? trying to think of the easiest way to fix it. Yeah. That's right. I think that's right. Okay. Yeah. Okay. So then we'll call this nmat, right? And then with that, we have that the strain vector is equal to dmat times jmat times nmat times the vector of unknown displacements. And then we call this B. Right. So then the strain is B times U. Okay? So that's where that came from. And I apologize. I think what that was around the time when I think because the Gauss integration those were videos that I assigned to you when I was on travel, and I guess I just assumed that I had covered this in the videos, and I didn't. The derivation is the same. I expect you're all graduate students. I expect you should be able to derive it yourself. And there's many other ways. As long as you're consistent with the mapping, you could have slight variations of what we did. You don't have to do it in sort of this matrix notation either. You could do it in a more direct indicial notation, and you wouldn't need so many sort of zeros that show up in here. Because we just use the zeros to kill entries that aren't used, right? And if you had a more direct indicial notation, you wouldn't have to do that. Yeah.
But that's not the case in C++, right?
Well, so in MATLAB, it's calling basically Fortran routines under the hood. That there's always a for loop somewhere. Yeah. It's just those for loops they're compiled code, right? And it's doing them in an optimized way. Same thing if you use Python and use the NumPy data structures. I mean, if you multiply a vector, an element-wise computation of a vector x times a vector y, you get back just an answer, but that computation is done by running through for loops that have been optimized in compiled code, right? And then, of course, any linear algebra operations that are done are typically calling into the systems BLAS and LAPACK libraries, right? So BLAS is basic linear algebra software that can do like your very efficient matrix vector multiplications and stuff like that. And then LAPACK comes with, typically works along with BLAS to do things like take inverses and LU factorizations and other things. So whenever you actually, write INV open parentheses A, under the hood it's calling BLAS to do probably an LU factorization and then an inverse operation. So the actual algorithm there is not even written in MATLAB. It's calling into compiled code. It's distributed with it. Yeah, so that's what I just construct. The D matrix is very, very explicit. Then I sort of construct because I compute these inverses of the 2 by 2 sort of by hand. This guy is pretty explicit too. And then on this one I just use that riffle feature where I'm taking the zeros and I'm riffling them in with the derivatives of the shape functions. Okay. Now if you're using a total Lagrangian setup, you only have to compute those derivatives of the shape functions at the integration points once up front, and you can store those values. So then it's pretty efficient. Now here, in this code, like we talked about before, I'm using an updated Lagrangian, so I actually recompute them every time. Okay, so the next thing I want to talk about